Hello, this is Nicholas again. I am sharing with you kind of a interesting problem that I saw and just did, and I really thought it was quite cool. The answer was kind of rather unintuitive. So I'm just gonna read it here real quick. A giant rabbit is tied to a pole in the ground by an infinitely stretchy elastic cord attached to its tail. A hungry flea is on the pole watching the rabbit. The rabbit sees the flea, jumps into the air, and lands 1 mile from the pole. So you got like pole, and then your rabbit jumps a mile, and then the flea sees that, jumps an inch. Okay. Okay. The rabbit sees the flea, jumps into the air, and lands 1 mile from the pole, with its tail still attached to the pole by the elastic cord. Okay. The flea gives chase and leaps into the air, landing on the stretch elastic cord 1 inch from the pole. The rabbit, seeing this, again leaps into the air and lands another mile away from the pole. A total of 2 miles from the pole. Undaunted, the flea bravely leaps into the air again, landing on the elastic cord 1 inch further along. Once the rabbit jumps another mile, and once again the rabbit jumps another mile, and the flea jumps another inch along the cord. If this continues indefinitely, will the flea ever catch up to the rabbit? And we have to assume the earth is flat and extends infinitely far in all directions, which we will see later why we need to assume that. So basically what we've got going on is if you imagine, here's the pole, right? And then you've got an elastic cord, and one end's tied to the pole. And so there's a rabbit and a flea at this pole. The rabbit jumps a mile, and the flea jumps an inch. I know, the rabbit can jump pretty far. And then the rabbit also must have really good vision, because he sees them all the way from almost a mile away jump an inch. And so then the rabbit jumps another mile, and then the flea jumps another inch, and then another mile, and then another inch, and then another mile, and another inch. So it looks like, it appears that the rabbit is just getting farther and farther and farther away from the flea, right? It doesn't look like the flea is gonna ever catch up to the rabbit, right? Well, that would be the case if the rabbit was not on this elastic rubber band, and the elasticity of the rubber band is key. So I'm going to try to illustrate to you why the elasticity is key. So I have a rubber band, okay, and you can see right here, say this dot represents the middle of the infinitely stretchy cord. All right, so this is about in the middle. Okay, now here's our midpoint. All right, now I'm gonna stretch this rubber band to about double its length, okay? And now watch what happens to this black point right here. All right, ready? Okay, now that's pretty cool, right? What's happened is the point relative to the total length of the rubber band or the proportion that the point has covered relative to the total length of the rubber band is still the same, right? It's still the midpoint, but relative to where we started here, we've moved. So in other words, when the rabbit jumps, the flea jumps with it. Not jumps with it, but the flea moves along with it relative to its position prior to the rabbit jumping. And that's a really cool fact, and that's gonna basically be the powerhouse of this problem is that particular fact that when you stretch the rubber band, you increase the flea's, in other words, the flea gets closer to the rabbit relative to where the flea was before. So the flea gains distance not only from its jumping an inch each time, but also it gains distance when the rabbit jumps as well. Okay. So, okay, now, basically, the proportion of the band that the flea has covered after the first cycle, right, so after the first cycle, in other words, the rabbit jumps and then the flea jumps, that's what I'm going to call a cycle. Okay, the flea, the flea has covered 1/63360 of the rubber band. And the reason why that is because there's 63,360 inches in a mile, basically, is what that comes down to. And maybe you didn't know that off the top of your head, but that's where that comes from. Okay. Now we imagine the rabbit is going to jump, but the flea's proportion of the rubber band that he's covered remains constant, but relative to his position before the rabbit has jumped, his position increases. Okay. So what happens basically is, then the flea is going to jump after that, making the total proportion that the flea has traveled along the rubber band after the second cycle being 1/63360 plus 1/2 times 63360. So basically, since the rubber band has doubled, then the rubber band has doubled in its length. So he's not going to travel another 1/63360 along the total proportion of the rubber band, but he's going to travel half of that because the rubber band has doubled from its original starting length, whatever length that was. Okay? So that's why there's this 2 right here, because the rubber band has stretched by a factor of 2, so he will only travel half that, right? It's inversely proportional. Okay. So now the rabbit jumps again, and again the flea's proportion that he has traveled along the rubber band relative to its total length is constant. But then the flea jumps another inch. So now we're at triple the length that we were at the first cycle. So now the proportion along the rubber band that the flea has traveled after 3 cycles of this is 1/63360 plus 1/2 times 63360 plus 1/3 times 63360. Again, because now the rubber band is 3 times its original length, so the flea will only travel 1/3 of what it did when it was its original length. Okay? Now hopefully you can kind of see a pattern. This will continue. After the nth cycle, the total proportion that the flea has traveled along the rubber band is 1/63360 plus 1/2 times 63360 plus 1/3 times 63360 plus or there'd be 1/4 times 63360, 1/5 times 63360 plus 1/n times 63360. Okay. And that's pretty cool right there. Now we want an n such that this infinite sum is greater than 1. Because then that's when the flea has surpassed the rabbit, right? Because we're talking about a proportion here. So if the flea travels all the rubber band, then this will equal 1. In other words, they're at the same spot along the rubber band. So when it's greater than 1, the flea has passed the rabbit. Okay. Now, I can rewrite this a little as 1/63360, that's a 6, times 1/1 plus 1/2 plus 1/3 plus 1/n. And we want this to be greater than 1 again. Okay. So, what we want then, okay, I'm gonna write this in sigma notation. 1 over 63360 sigma n equals 1 to k of 1 over n. And if it's equal to 1, then they are, then basically what's happening is that the flea and the rabbit are at the same place, right? They both traveled the total proportion of the rubber band. So what I'm going to do is I'm going to set this equal to 1. I'm going to find a value n that makes this 1. And then what I'm going to do is just say, well, pick an n greater than the value when it's 1, and that's when the flea passes the rabbit. Okay, so 63360 is equal to sigma n equals 1 to k, 1 over n, right? Multiply both sides by 63360. Now, you may recognize this, which is the same thing as this, as it's a very famous series. It's called the harmonic series. If you alternate between plus or minus signs, then what you get is what's called the alternating harmonic series, which you can actually, if you kind of fool around with the parentheses sum, get it to converge to any value you want. If you keep it how it is the same, right, 1 minus a half plus a third minus a fourth, you'll get that converges to the natural log of 2. Anyway, so this harmonic series, right? You might think it converges, in other words, tends towards a fixed value, because what's happening here is your denominators are getting smaller, right? Right, like if you have like 1 plus a half plus a fourth plus an eighth, dot, 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 and you go on and on and on, right? That's equal to 2. But in this particular case, and this is one of the reasons why it's kind of famous, is that this series actually diverges. It as you keep adding terms, it just goes off towards infinity. And I'm going to try to provide I'm going to try to provide 2 proofs as to why that is. This one I've kind of created on my own. I can't really find it anywhere else. And then another way is kind of the standard way of proving that it diverges. So the way that I came up with is basically you break it up into a bunch of other you break it up into infinitely many infinite series. So you have sigma n equals 1 to infinity of 1 over n is equal to 1 plus sigma n equals 1 to infinity of 2 over n plus sigma n equals 1 to infinity of 3 over n, 3 to the n. I'm sorry, 1 over 2 to the n, 1 over 3 to the n. I'm sorry, that might have confused you a little bit, I'm sorry. So basically what I'm doing is I'm taking all the powers of 2, right? Because like a half will be in here, a fourth will be in here, an eighth will be in here, 16th. All the powers of 2 will be in here. So and then I have the 1 here out front. I'm taking powers of 3s, right? 3, 9, 27, 81, 243. Those will all be in there, right? And then now normally I would write sigma. Well, I am gonna be writing a sigma n equals 1 to infinity again. But I'm not gonna write 1 over 4 to the n here, because all the powers of 4 are all powers of 2. So you'd be overlapping. So you just need the powers of 2 in there. Now I'm going to do 1 over 5 to the n plus sigma n equals 1 to infinity. Now, the powers of 6s, let's see. The powers of 6s you do need to do, right? Because right, powers of 6 is 6, 36, 216, and 1256 I think is next. Those are not included in your powers of 2 and your powers of 3. So 6, keep forgetting the 1 over 16 plus sigma. Oh, and hopefully, I'm just going to write one more. Hopefully you can kind of see what I'm doing now. 1 over 7 to the n plus ... And now I wouldn't include the 8s here after this, 1 over 8 to the n, because all the powers of 8 are powers of 2. And then I wouldn't include the 9s because all the powers of 9s are powers of 3s. I would include the 10s though. Okay. So. Okay. Now, let's evaluate each one of these infinite converging geometric series. And we know these converge because you have a common ratio that is less than 1. Common ratio less than the absolute value of 1, which is less than 1. So 1 plus, now 1 over 2 to the n, right? If we start with 1, we get a half plus a fourth plus an eighth plus a 16th. And if you remember, the sum of an infinite converging geometric series is given by the first term, a sub 1 over 1 minus r, the common ratio. And the way you can kind of remember why that is because the sum of the first n terms of any geometric series is a... Oh gosh. I'm gonna... I forget that one. I believe it's a sub 1 times 1 minus r to the n over 1 minus r. Yeah, it is. Okay. And so what you're doing then, if you have an infinite geometric series, is you're letting n get bigger and bigger. In other words, the number of terms approaches infinity. So if we take the limit as n approaches infinity of s sub n, that's an s, of s sub n, that's equal to the limit as n approaches infinity of a sub 1 times 1 minus r to the n over 1 minus r. Now notice, this is a constant, okay? Now, what we're going to do, since we're dealing with converging geometric series, is we're going to let the absolute value of r be less than 1. In other words, r is somewhere between -1 and 1. Okay, now n is approaching infinity, so n's getting bigger and bigger. Now, when you raise a number that is somewhere between -1 and 1, and you keep on, and you keep on repeating, like, take a half, for example, right? Say your common ratio is a half, and in our case it is. A half times a half is a fourth, times another half is an eighth, times another half is a 16th, times another half is a 32. Yeah, then it goes on and on. In other words, if you raise a number somewhere between -1 and 1 to an exponent that gets increasingly large, your number approaches 0. Okay, and pick any number between -1 and 1 if you still don't believe me. So basically, you get a sub 1 times 1 minus 0 over 1 minus r. And obviously, 1 minus 0 is 1, so a sub 1 over 1 minus r. That's where that formula comes from. Okay, so now we've established that. So this first sum here is given by 1/2 over 1 minus a half, plus, and then this one here is given by 1/3 over 1 minus 1/3, and this is 1/5 for 1 minus 1/5, plus 1/6 or 1 minus 1/6, plus ... Okay, now we get 1 plus, now we have 1/2 over 1/2, which is 1. Anything over itself is 1 except for 0. Now we get 1/3 over 2/3, which is 1/2. And now we get 1/5 over 4/5, which is 1/4. And then 1/6 over 5/6, which is 1/5. And then if we were to evaluate the one for 7, we get a 7th over 6/7, which is a 1/6. Okay. Now, this does look somewhat familiar, right, to this series here, right? These two look familiar, but this term, right, this one is missing the third. It's missing, right, it's missing the third. It will basically miss all the fractions whose, powers are in common. In other words, right, like here we didn't have to include 1 over 9 to the n because all the powers of 3 are powers of 9. And so you end up missing an infinite amount of terms that this one has because of that. But by definition, this and this are they are equivalent. And we've just shown through this that this is equal to that. And since this, by definition, is that, which we have shown is that, these two, which we have just shown to be equivalent, are missing, this one is missing an infinite amount of terms that this one has, okay? Now, there are either two things that series can do. It can either converge, right? It can either tend towards a fixed value, or it can diverge, go off towards infinity, okay? Now, let's say that they both converge. Well, that's impossible. They both cannot converge because the second sum, which is equivalent to the first one, is missing an infinite amount of terms that the first sum has, right? This first term has an infinite amount of terms that the second term is lacking. So, if these were to converge, then they would converge to different values because they have different terms. But that's impossible because we've just shown that these two are the exact same sum. Therefore, since you can't have two identical sums converge to two different values, both of them must diverge. So, the harmonic series diverges is basically what I'm getting at here. Okay. Now, basically that's really pretty much the thing you need to prove in this problem to show that the flea can in fact catch up to the rabbit. Now, if you know that series diverges, meaning it goes off towards infinity, then for some very large n in that summation there, it will surpass 63,360. So, the answer to the question, will the flea ever catch up to the rabbit, is yes. And we're done.